Something enormous is pulling our galaxy through the void. This is the Great Attractor, a gravitational mystery hidden behind the curtain of our own Milky Way. It is just one secret within a hidden architecture that spans the cosmos, a vast cosmic web of filaments, walls, and voids that dictates the fate of everything we see. By the end of this journey, you will understand the true structure of the universe and our surprising place within it. We will uncover why half of all normal matter was missing for decades, and whether we are sailing toward a cosmic metropolis or into an endless dark. What does it feel like to live inside a mystery this vast? Our galaxy is not drifting freely through space. It is being hauled at a breathtaking speed of over 600 kilometers every single second toward a point of darkness we cannot even see. This is the first and most fundamental secret, the invisible cosmic magnet we call the Great Attractor. But to call it a single object, a giant black hole, or a monstrous star is to misunderstand its true nature. It is something far more diffuse and yet more powerful. It is a region of space, a gravitational focal point, where the mass of an entire supercluster of galaxies has pooled together. Picture the gentle slope of a valley gathering rainwater from miles around. The Great Attractor is that valley on a cosmic scale, its immense gravity warping the very fabric of space-time, creating a downhill slope that our local group of galaxies and thousands of others are sliding down. This anomaly hides in the constellation of Norma near the heart of our galactic plane, and that location is the key to its secrecy. From our vantage point on Earth, we must peer directly through the crowded, dusty core of the Milky Way to see it. Astronomers call this our zone of avoidance, a thick band of stars and gas that blocks our view of nearly 20% of the distant universe. For decades, the Great Attractor was a ghost felt but not seen. Its presence was first inferred in the 1970s, not by a telescope capturing its light, but by measuring a strange discrepancy in the motions of galaxies. Scientists were mapping the universe's expansion, expecting every galaxy to be moving smoothly away from us in the aftermath of the Big Bang. But they found a peculiar velocity, a mysterious drift superimposed on that universal flow. Our entire galactic neighborhood was being tugged off course, suggesting something with the gravitational pull of 100,000 Milky Ways was lurking in the shadows. This discovery reshaped our cosmic map. We realized we are not the center of anything, but rather passengers on a vast river of galaxies, all streaming toward a hidden destination. The Great Attractor is the first undeniable proof that the universe's large-scale structure has a powerful, local influence, that even the grand motion of galaxies can be steered by unseen concentrations of mass. It forced a humbling admission that some of the most important landmarks in the cosmos might be sitting right in our blind spot. This relentless pull toward the Great Attractor is not our only motion. It is merely the strongest current in a far grander river system. Our galaxy's ultimate destination is a layered journey, a cosmic voyage nested within ever larger structures. First, we are part of a small, gravitationally bound family called the Local Group, which includes the Andromeda Galaxy and dozens of smaller satellite galaxies, all orbiting a common center of gravity. This entire family, in turn, is falling toward the heart of our local supercluster, the Virgo Supercluster, a sprawling collection of perhaps 100 galaxy groups centered on the massive Virgo cluster. Think of it as a leaf, our local group, caught in a gentle stream flowing toward a large pond. But that pond itself is not still. The entire Virgo supercluster, our local pond, is being tugged by an even greater concentration of mass, the Hydra Centaurus supercluster, which lies closer to the Great Attractor. So our motion is a compound one, a gentle drift within a family, within a larger flow, within a titanic river. We are like a passenger on a boat sailing down a wide river, the boat itself drifting with the current while the entire river system slopes toward a distant ocean. The Great Attractor is that ocean's deepest basin, the final gravitational sink for this entire region of space. This multi-tiered flow reveals a profound truth about the universe's structure, that gravity operates on every scale, from apples falling to entire superclusters of galaxies sliding down gentle slopes in the fabric of space-time. Our journey is not a frantic rush but a stately, inevitable drift, one that has been underway for billions of years and will continue for billions more. Where exactly is this river taking us? The very thing that makes our night sky beautiful is what keeps us in the dark. This is the third secret, our own cosmic blind spot known as the zone of avoidance. It is not a void out in space, but a thick, obscuring wall created by the disk of our own Milky Way galaxy. When we look toward the constellations of Sagittarius, Scorpius, and Norma, where the Great Attractor lies, we are staring directly through the crowded, dusty plain of our galactic home. Imagine trying to see a distant city skyline through a dense, permanent fog, one filled with the glare of countless streetlights. That is our view. The light from billions of distant galaxies is absorbed or scattered by interstellar dust and drowned out by the sheer density of foreground stars. For traditional optical telescopes, this band across the sky is a frustrating dead zone, concealing nearly a fifth of the entire universe from our direct view. It is the ultimate cosmic irony that to see one of the largest structures influencing us, we must first find a way to see through ourselves. Astronomers, however, are masters of adaptation. When one window to the universe closes, they simply open another. To penetrate this veil, they turn to light our eyes cannot see. Infrared light, with its longer wavelengths, can slip between dust grains that block visible light. Projects like the 2-micron All-Sky Survey, or 2MSS, mapped the entire sky in infrared, revealing the faint glow of stars and galaxies hidden behind the Milky Way's dust. It was like switching from a regular flashlight to a heat vision camera. Suddenly, the outlines of hidden structures began to emerge, but to find the true mass, the gravitational anchors, they needed another tool. They looked to X-rays, extremely hot gas heated to millions of degrees, gathers in the vast spaces between galaxies in a cluster and glows brightly in X-ray light. Satellites like ROSAT scanned the zone of avoidance, not looking for stars, but for these immense hot halos. Where they found a bright, diffuse X-ray glow, they knew they had found a massive cluster of galaxies, its gravity holding the superheated gas in place. By piecing together the infrared starlight and the X-ray halos, astronomers could finally trace the skeleton of the hidden universe. They confirmed that the Great Attractor is not a single, impossible object, but the dense core of a colossal supercluster, its true form masked by our own galaxy's sprawl. This technical triumph did more than just reveal a hidden landmark. It proved that no mystery, no matter how well hidden, is completely safe from our curiosity. But the story of our cosmic drift does not end with the Great Attractor. As astronomers peered deeper into the infrared and X-ray data, piercing further through the zone of avoidance, they found something even more colossal waiting in the shadows. This is the fourth secret, the Shapley Attractor. Located over 600 million light-years beyond the Great Attractor, the Shapley supercluster is the single largest concentration of mass in our observable cosmic neighborhood. It is not merely a cluster of galaxies, but a supercluster of superclusters, a titanic knot in the cosmic web containing perhaps 10,000 times the mass of our Milky Way. For a moment, this discovery seemed to solve everything. The Great Attractor, immense as it is, might just be a local landmark, a rest stop on a highway leading to a far greater destination. Our entire local flow, the so-called bulk flow of galaxies, could simply be the universe falling toward Shapley's overwhelming gravity. The debate ignited immediately. Is the Great Attractor the main event, or is it merely a signpost pointing to Shapley? The answer, as it often is in cosmology, is likely both. Think of it like water draining from a vast landscape. The Great Attractor is a major regional basin collecting water from the hills and valleys around us. But that basin itself sits on a continental slope that tilts everything toward the deepest ocean trench, which is Shapley. Both gravitational influences are real and both are acting on us simultaneously. Our motion is the sum of these tugs, a complex dance dictated by the entire mass distribution of the nearby universe. This bulk flow, the coordinated movement of thousands of galaxies across hundreds of millions of light years, is one of the most powerful pieces of evidence we have for the large-scale structure of the cosmos. It tells us that gravity's reach is staggeringly long, and that empty space is not empty at all, but sculpted by hidden mountains and valleys of dark matter and galaxies. The ongoing scientific quest is to precisely weigh these distant attractors, to map the subtle gradients in our motion and pinpoint what fraction of our journey is due to each colossal structure. It is a reminder that in an expanding universe, even recession has a local direction, steered by the greatest concentrations of mass hiding in the darkness. The true nature of the Great Attractor's power points to a deeper, more pervasive mystery. The visible galaxies we have painstakingly mapped in that hidden region, immense as they are, simply do not add up to the gravitational force required to pull us so relentlessly. This is the fifth secret, the invisible hand shaping the cosmos. The anomaly of the Great Attractor is not just evidence of hidden galaxies, it is direct proof of dark matter's overwhelming presence. To account for the pull we feel, astronomers calculate that the region must contain far more mass than all its stars, gas, and dust combined. The Great Attractor, therefore, is not primarily a collection of bright galaxies, but the dense, beating heart of a titanic halo of this unseen substance. Picture a magnificent city at night, its glowing skyscrapers and streetlights tracing the outlines of its neighborhoods. Now imagine that this entire city is built upon a mountain of dark, dense rock 10 times larger than the city itself. The glowing lights are the galaxies, but the mountain, invisible to our eyes, is the dark matter that defines the landscape and dictates where the city can be built. The gravitational pull we measure is the pull of that entire mountain, not just the sparkling city on its peak. This realization weaves the Great Attractor directly into the grandest narrative of modern cosmology, the story of the universe's missing mass. Dark matter, which does not emit, absorb, or reflect light, interacts with the universe only through gravity. It is the universe's hidden skeleton. In the early cosmos, slight ripples in the density of dark matter provided the gravitational wells into which normal matter, the gas that would become stars and galaxies, could later flow. The Great Attractor is one of the most significant local examples of this process, a place where the dark matter skeleton is so massive it has drawn in a spectacular concentration of visible matter. So when we speak of being pulled toward the Great Attractor, we are really talking about being pulled by the gravitational influence of a vast, unseen architecture, a scaffold of dark matter upon which the luminous universe is merely draped. This hidden framework is what truly organizes the cosmos into the vast web of filaments and voids, guiding the formation of superclusters and dictating the motion of galaxies across billions of light years. The Great Attractor, then, is a cosmic signpost pointing not just to a place, but to a fundamental truth that most of the universe's material influence is utterly invisible to us. This discovery of dark matter's hidden architecture forced a complete reimagining of our cosmic map. If the Great Attractor was a mountain in the dark, then what other colossal structures were waiting to be found? The answer arrived with a shock, a structure so vast it shattered the long-held assumption that the universe was smooth on the largest scales. This is the sixth secret, the existence of the Great Wall. In the late 1980s, astronomers Margaret Geller and John Huckrow were leading a project to map the three-dimensional positions of galaxies, a survey known as the Center for Astrophysics Redshift Survey, or CFA2. As they plotted the distances of thousands of galaxies, a pattern began to emerge that was far from random. the galaxies were not sprinkled evenly across the cosmos like dust. Instead, they were arranged in a staggering, thread-like structure, a contoured wall of galaxies stretching over 500 million light-years across the sky. They named it the CFA2 Great Wall. To grasp its scale, consider that a beam of light traveling from one end to the other would take more than twice as long as the entire history of animal life on Earth. This wall was not a solid barrier, but a filament, a dense river of galaxy clusters and groups intertwined with vast, empty chambers. Its discovery was a monumental moment in cosmology. For decades, the prevailing principle had been the cosmological principle, which stated that on sufficiently large scales, the universe should look roughly the same in every direction, a homogeneous and isotropic soup of matter. The Great Wall stood in direct defiance of that idea. Here was proof that clumping, the tendency of matter to gather under gravity, did not stop at the size of galaxy clusters. It operated on a scale previously thought impossible, weaving the universe into a web of structures with features larger than any scientist had dared to predict. It was the first direct observational evidence of the cosmic web in action, a blueprint of the universe's large-scale skeleton written in starlight. The Great Wall revealed that our cosmos is fundamentally lumpy, organized into an architecture of breathtaking grandeur, where galaxies are merely the illuminated nodes in a dark matter framework of inconceivable size. Finding this wall meant we were no longer just mapping stars, we were mapping continents in space. The discovery of the first Great Wall was just a glimpse. To truly understand the architecture of the cosmos, we needed a map of unprecedented scale and precision. This need gave birth to one of the most ambitious astronomical projects in history, the Sloan Digital Sky Survey. Beginning in the year 2000, this survey did not just look at the sky, it meticulously catalogued it. Using a dedicated telescope equipped with a massive digital camera, Sloan systematically imaged and measured the distances to millions of galaxies, painting a three-dimensional portrait of the universe that stretched back in time over 5 billion light-years. Where earlier surveys had sketched the outlines of a single wall, Sloan revealed the full tapestry. Its map showed the cosmic web in staggering detail, a labyrinth of galaxy filaments, dense knots of clusters, and vast, echoing voids. It was like switching from a hand-drawn map of a single mountain range to a satellite image of an entire continent, with every river, valley, and peak laid bare. The survey's most famous and controversial discovery was a structure that dwarfed the original Great Wall, the Sloan Great Wall. This filament is a staggering 1.4 billion light-years in length, a chain of superclusters so immense it seemed to challenge our very understanding of how large anything in the universe could possibly be. For years, it held the title of the largest known structure in the observable universe. Sloan's legacy, however, is far greater than any single record. It provided the definitive evidence that the cosmic web is the fundamental organizing principle of the universe. The survey showed that galaxies are not randomly scattered. They are precisely tracing the underlying dark matter scaffolding, clinging to the dense filaments like dew on a spider's web. This map allowed scientists to move from simply finding structures to studying their statistics, to understanding the rules that govern how gravity assembles the universe on the grandest scales. It turned cosmology from a science of singular wonders into a rigorous study of cosmic architecture, proving that the emptiness of space is an illusion and that we live within a structured, connected, and breathtakingly complex web. But the Sloan map was only a snapshot of one region. To grasp the true blueprint of the universe, we must step back and see the pattern in its entirety. This is the cosmic web, the fundamental architecture that governs everything we have discussed. It is not a metaphor, but the actual large-scale structure of the observable cosmos. Picture the universe not as a starry soup, but as a colossal, three-dimensional sponge. The dense, solid material of the sponge represents the filaments, the long, interconnected threads where galaxies and galaxy clusters are packed together. The holes in the sponge, the vast empty spaces, are the cosmic voids, and where multiple filaments intersect, you find the densest knots, the great superclusters and attractors that act as gravitational anchors. This web is the result of gravity's relentless work over nearly 14 billion years. In the early universe, tiny quantum fluctuations were stretched to cosmic proportions by the Big Bang's rapid expansion. These subtle ripples in density became the seeds for all future structure. Slightly denser patches of dark matter exerted a stronger gravitational pull, drawing in more dark matter and eventually the normal gas that would form stars and galaxies. Over eons, this process created a vast network, with matter flowing along the dark matter scaffolding like water converging into rivers, leaving behind ever-growing deserts of emptiness. The most compelling evidence for this web comes from comparing two kinds of maps. On one side, we have the real observational data from surveys like Sloan, with each point of light representing a real galaxy whose position has been painstakingly measured. On the other side, we have supercomputer simulations of the universe's evolution, which begin with those initial ripples and let the laws of physics play out over virtual billions of years. The results are uncanny. The simulated universes consistently produce the same sponge-like, filamentary structures that we observe in the real data. This match is one of the great triumphs of modern cosmology, a powerful confirmation that our understanding of gravity, dark matter, and cosmic evolution is fundamentally correct. The cosmic web explains the Great Attractor and the Great Walls not as isolated anomalies, but as natural features of this universal blueprint. The Great Attractor is a major node, a dense knot where several thick filaments converge. The Great Walls are segments of the filaments themselves, viewed edge-on. Even our own Milky Way resides within a filament, a minor thread feeding into the larger structure of the Laniakea supercluster. This realization redefines our place in the cosmos. We are not simply in a galaxy within a group within a supercluster. We are inhabitants of a specific strand in a universal web, our local motion dictated by the gentle gravitational slope of the filament we are embedded within. The entire history of galaxy formation, collision, and migration has been choreographed by this invisible framework. So when we look up at the night sky, we are not looking at a random scattering of stars, but out through the intricate lattice of our local filament, toward the glowing nodes and dark voids of a structured universe whose full majesty we are only beginning to comprehend. The cosmic web's filaments define its structure, but its true scale is measured by what is not there. Between every great wall and shimmering supercluster lie the voids, the emptiest places in existence. These are not small pockets of nothing, but staggering deserts of space, some stretching over 300 million light-years from end to end. If our Milky Way galaxy were the size of a grain of sand, a typical void would be an empty sphere the size of a football stadium. Within them, galaxies are almost non-existent or huddle in lonely, isolated threads against the overwhelming emptiness. The most famous of these is the Boötes Void, discovered in the 1980s. At its heart, this colossal sphere of near-nothingness contains only a handful of galaxies where a typical region of that size would hold thousands. Finding it was like mapping a continent and discovering a country-sized hole in the middle of the ocean, a place where the rules of cosmic geography seem to break down. These voids are not accidents, they are fundamental features. They are the negative space in the universe's grand design, the inevitable result of gravity's work. As matter drained over billions of years from the low-density regions into the high-density filaments and nodes, it left behind these ever-growing bubbles of near vacuum. But a void is not completely empty. It contains trace amounts of extremely diffuse gas and presumably the ubiquitous dark matter, though at a density far lower than the cosmic average. Their profound emptiness makes them something far more valuable than just cosmic curiosities. They are pristine laboratories for studying the universe itself. Because there is so little inside them to create local gravitational distortions, voids expand with the purest rhythm of the universe's underlying expansion. They are like perfect, empty balloons whose growth is dictated solely by dark energy, the mysterious force accelerating the cosmos. By measuring how voids grow over time, cosmologists get a clean read on the strength of dark energy and the geometry of space-time. Furthermore, the pattern of voids, their sizes and distribution, acts as a cosmic fossil record. That pattern encodes information about the universe's earliest moments, the nature of the initial ripples, and the properties of dark matter. So, while we are drawn to the glittering cities of the cosmic web, the silent, expanding deserts between them hold the keys to the universe's deepest secrets and its ultimate fate. These vast voids are defined by what surrounds them, the luminous threads of the cosmic web. Filaments are the universe's true superhighways, the dense channels where normal matter, and therefore galaxies like our own, are concentrated. While the dark matter skeleton is invisible, the filaments are traced in light by the countless galaxies that have formed along them, like streetlights illuminating a freeway at night. Our Milky Way does not float in an open sea of emptiness. We are embedded within a modest filament ourselves, a local strand of the web that connects our local group to the vast Virgo cluster and beyond. This placement is not a cosmic accident. Filaments are the primary environments for galaxy formation and evolution. They act as colossal conduits, funneling vast rivers of primordial gas from the voids into the hungry nodes where galaxy clusters form. This continuous flow is the lifeblood of the cosmos, providing the fuel for new stars to ignite and for existing galaxies to grow. To understand this process, we must peer into the spaces between the galaxies themselves, into the intergalactic medium that fills these filaments. This is a diffuse ocean of mostly hydrogen and helium gas, so thin that by earthly standards it would be considered an exquisite vacuum. Yet spread across the staggering volume of a filament, it contains an enormous amount of the universe's normal matter. Studying this ghostly material directly is a profound challenge, as it emits almost no light of its own. Astronomers, therefore, use a brilliant trick of cosmic backlighting. They look at the most luminous beacons in the distant universe, quasars. As the intense light from a quasar travels billions of light years to reach us, it passes through the filaments of the cosmic web. Atoms within the filament's gas absorb specific, precise wavelengths of that light. When the quasar's spectrum is finally captured by our telescopes, it is scarred by a thicket of dark absorption lines, a veritable forest of missing light. This pattern, known as the Lyman alpha forest, is a unique barcode. Each line corresponds to a different cloud or strand of hydrogen gas at a specific distance along the line of sight. By decoding this forest, scientists can map the distribution and temperature of the intergalactic medium in astonishing detail. They can trace how this gas is structured into sheets and filaments, and measure how it flows from the emptier regions into the denser knots of the web. This faint absorption pattern is our direct evidence of the universe's plumbing system, revealing the invisible rivers of fuel that have been feeding galaxies since the dawn of time. It confirms that the beautiful structure we see in galaxy surveys is just the glittering trace of a far more extensive and mostly hidden circulatory system. The cosmic web's filaments do not simply drift apart. They converge into the most magnificent gatherings of matter in the universe. These are superclusters, the sprawling galactic metropolises where gravity has woven together entire clusters and groups of galaxies into a single, tenuous structure. For most of astronomical history, our understanding of these titans was murky, defined by vague boundaries and confusing maps. That changed in 2014 with a revolutionary discovery about our own cosmic neighborhood. We learned our true address, and it is called Laniakea. This Hawaiian word means immeasurable heaven. and it is a fitting name for a structure 100,000 galaxies wide, spanning over 500 million light-years. Laniakea is not just a list of nearby clusters, it is a watershed in space. Scientists defined it by mapping the subtle flow of galaxies, tracing how every group, including our own local group, is sliding down the same gravitational slopes toward a common center of attraction. That center is the Great Attractor, so the Virgo supercluster we once called home, the Hydra Centaurus supercluster, and the Norma cluster are all just provinces within this single, vast supercluster, all tributaries flowing into the same Great Basin. This redefinition was profound. It showed that superclusters are defined not by static borders, but by motion, by the shared destiny of everything within their gravitational domain. Within Laniakea, every galaxy is ultimately connected by this slow, stately river of space, all journeying toward the same invisible focal point. Yet, for all their grandeur, superclusters embody a cosmic contradiction. They are the largest structures that gravity can loosely bind together, but they are not permanent. Their immense size works against them. The galaxies within a cluster like Virgo are tightly bound, destined to orbit each other forever. But the clusters within a supercluster like Laniakea are so far apart that the space between them is expanding. Here, the relentless force of dark energy, which drives the universe's acceleration, begins to win. Over tens of billions of years, dark energy will stretch the fabric of space within the supercluster itself. The gentle gravitational ties that link its far-flung clusters will be overcome. The great rivers of galactic flow will slow, then reverse. Laniakea and all superclusters like it will be torn apart from the inside out, their constituent clusters left isolated in a rapidly expanding void. So we live in a fleeting moment of cosmic architecture within a magnificent city that is still gathering its suburbs, even as the foundation beneath it is being pulled away. This grand architecture of filaments and voids does more than just organize galaxies. It can subtly distort our very perception of the cosmos. One of the most pressing mysteries in modern astronomy is a discrepancy known as the Hubble tension. At its heart, it is a conflict between two ways of measuring how fast the universe is expanding. When we look at the local universe using pulsating stars called Cepheids and exploding stars known as Type 1, a supernova, we get one expansion rate. When we look at the ancient light from the cosmic microwave background, the afterglow of the Big Bang, we get a slightly slower but incredibly precise expansion rate. These two gold standard methods should agree, but they do not. The difference is small, only a few percent, but in the precise world of cosmology, it is a glaring signal that something in our understanding is amiss. This is where the large-scale structure we have been exploring enters the story. Our local measurements are not taken from a perfectly still, average point in space. We are observers caught in a river, the bulk flow, that coordinated drift of thousands of galaxies toward the Great Attractor and beyond, means our entire local neighborhood has a peculiar velocity superimposed on the universe's smooth expansion. Think of trying to measure the speed of a river's current while you are standing on a raft that is also drifting with a gentle breeze. If you do not account for the breeze, your measurement of the river's speed will be slightly off. In the same way, if we do not perfectly account for our own motion within the cosmic web, our local measurement of the universe's expansion could be biased. Some cosmologists suggest that we might live in a region that is slightly underdense, a local bubble that is expanding a bit faster than the cosmic average because there is less gravitational pull holding it back. This would mean our local measurement is not wrong, but simply local, reflecting the conditions of our filament and our supercluster. The tension, then, could be a clue that the universe is not as uniform as we assumed, that the cosmic web introduces wrinkles in expansion itself. While this bulk flow effect is likely too small to explain the entire discrepancy, it forces a profound realization that to measure the cosmos, we must first understand our precise motion within its grand and flowing architecture. The universe carries its own indelible fingerprint, a pattern of sound frozen into its very structure. These are Barrian acoustic oscillations, the fossilized echoes of the cosmos's first 380,000 years. In that primordial era, the universe was a searing, opaque plasma, a soup of particles and light so dense that photons could not travel freely. Within this churning fluid, gravity tried to pull matter together into clumps while the intense pressure of radiation pushed it apart. This created a tug-of-war, generating powerful sound waves that rippled outward from every slight over density, like the concentric rings from a stone dropped in a pond. But this pond was the entire observable universe, and the ripples moved at over half the speed of light. Then, in a flash, the universe cooled enough for atoms to form. The fog cleared, the photons decoupled from matter and streamed free as the cosmic microwave background, and the sound waves instantly froze in place. They left behind a subtle but permanent signature, a preferred scale imprinted on the distribution of matter. The radius of those frozen ripples, the distance the sound wave could travel before the universe became transparent, became a cosmic standard ruler. That ruler is exactly 490 million light-years long. This means that if we could map all the galaxies in the universe, we would find a subtle statistical excess of galaxy pairs separated by this specific distance. It is as if the early universe stamped every structure with a faint watermark, a recurring spacing that whispers of its violent infancy. For cosmologists, this is a gift of unimaginable precision. Unlike other cosmic measuring tools that can be dim or distorted, this standard ruler is engraved across the entire sky, woven into the fabric of the cosmic web itself. By conducting massive galaxy surveys like the Sloan Digital Sky Survey and its successor, the Dark Energy Spectroscopic Instrument, or DESI, scientists can measure this scale at different epochs in cosmic history. They look deep into space and thus back in time to see how the apparent size of this ruler has changed. Because we know its true physical size, any difference we see in its angular size on the sky tells us exactly how much the universe has stretched in the intervening billions of years. This allows us to reconstruct the expansion history of the cosmos with breathtaking accuracy, tracing how the rate of growth has changed under the competing influences of gravity and dark energy. These fossil ripples are therefore our most reliable tool for constraining the nature of dark energy itself, offering a direct measurement of how its repulsive force has shaped the destiny of everything. Our cosmic address may be more unusual than we ever suspected. The very maps that revealed Laniakea and the cosmic web have also hinted at a startling possibility that our Milky Way galaxy does not reside in an average region of space. We might be floating in a cosmic hole. This is the 14th secret, the KBC Void, named for the astronomers Keenan, Barger, and Cowie who proposed its existence. Their analysis of galaxy survey data suggests we live inside a vast spherical underdensity, a bubble of space that is significantly emptier than the cosmic average. This proposed void is staggering in scale, perhaps 2 billion light-years across, making it one of the largest potential structures ever identified. Inside this bubble, the density of galaxies and matter could be as much as 20% lower than the rest of the universe. If true, this fundamentally challenges a cornerstone of cosmology, the cosmological principle, which assumes that on large enough scales the universe is smooth and homogeneous, that no place is special. Our location would be special, a quiet backwater in the grand cosmic metropolis. The implications ripple outward, touching one of astronomy's greatest puzzles. Living in an underdensity would mean the gravitational pull on our local region is weaker. With less mass holding it back, the space inside our bubble would expand faster than the denser universe outside. When we measure the expansion rate using nearby supernova and other local markers, we are measuring that faster local rate. This could provide an elegant, if controversial, solution to the Hubble tension. The discrepancy between the local and early universe expansion rates might not be an error in our physics, but a simple error in our perspective. We have been measuring the universe from inside a slightly runaway balloon, mistaking its local inflation for the global rule. This idea places the KBC void at the heart of a fierce scientific debate. Is it a real physical structure or merely a statistical fluke in our galaxy surveys? Critics argue that the evidence is not yet strong enough, that incomplete data or selection biases could create the illusion of a void where none exists. Proponents point to independent observations like the peculiar motion of our local group, which seems consistent with a flow out of an underdense region. The controversy is a beautiful example of science in action, a battle of data and interpretation that forces us to question our most basic assumptions. Are we truly typical observers in a uniform universe, or have we, by cosmic chance, spent our entire history looking out from an extraordinary vacancy? The answer reshapes not just our maps, but our entire philosophical place in the cosmos. Even the cosmic microwave background, that pristine snapshot of the infant universe, carries a faint shadow of motion. In the early 2000s, astronomers studying this afterglow made a deeply puzzling discovery. They were analyzing data from the Wilkinson Microwave Anisotropy Probe, a satellite that had mapped the subtle temperature variations in the cosmic microwave background with exquisite detail. These tiny hot and cold spots, millionths of a degree in difference, are the seeds of all future structure, but the scientists noticed something strange. There appeared to be a subtle, yet statistically significant, dipole in the motion of entire galaxy clusters. These massive clusters, each containing thousands of galaxies, seemed to be streaming in a coherent direction, a vast, slow current on top of the universe's expansion and the local bulk flows we already knew about. They called it the dark flow. The mystery was not just the motion itself, but its apparent source. This streaming seemed to extend far beyond the reach of any known concentration of mass, even beyond the Shapley attractor. According to our standard models, nothing outside our observable universe should be able to exert a gravitational pull on what is inside, as the expansion of space severs such connections. Yet the data hinted that thousands of galaxy clusters were all drifting toward a single point on the sky, as if tugged by something unimaginably vast and distant. The implications were staggering. Could the dark flow be evidence of a pre-Big Bang structure, a remnant of some earlier cosmic phase whose gravitational imprint still echoed into our own? Or perhaps it was a sign of something even more profound, a tilt in the very fabric of space-time caused by our universe being born in a lopsided manner. The scientific community erupted with both excitement and skepticism. Critics argued fiercely that the signal was an artifact, a systematic error in how the data from the satellite was processed, or perhaps an effect of our own complicated motion through the local web being imperfectly subtracted. They pointed out that measuring the peculiar velocity of distant clusters using the cosmic microwave background is an extraordinarily delicate task, akin to detecting the drift of a boat by measuring the microscopic ripples it leaves on a vast stormy ocean. The debate raged for years, with follow-up studies from other instruments providing conflicting results. Some supported the original finding, others found no evidence at all. The truth, as it often does, likely lies in a more nuanced interpretation. The most widely accepted explanation today is that the dark flow, to the extent it exists, is not a mysterious pull from beyond the horizon, but a reflection of our own motion through the cosmos relative to the rest frame of the cosmic microwave background. We are not still observers. Our local group, our supercluster, all of Laniakea, is in motion. This creates a Doppler shift in the ancient light, a kind of cosmic headwind. When we try to measure the motions of distant clusters, we must first subtract our own movement from the equation. If that subtraction is even slightly imperfect, it can leave behind a ghostly pattern that looks like a universal flow. This connects the dark flow mystery directly back to the attractors we have already met. Our motion is the sum of all the gravitational tugs from Virgo, from the Great Attractor, from Shapley. If we have underestimated the mass or influence of any one of these colossal structures, or if there is another, even larger concentration just beyond our current maps, then our calculated motion would be wrong. The apparent dark flow could simply be the gravitational pull of unseen attractors, their full magnitude not yet accounted for in our models of the local universe. It becomes a tantalizing clue, not necessarily to a pre-Big Bang realm, but to the possibility that our census of the cosmic web is still incomplete, that there are mountains in the dark even larger than we have dared to dream. But if superclusters like Laniakea are the largest bound structures, what is the absolute limit? This brings us to a foundational cosmic rule and the secret of its potential violation. The cosmological principle states that on the very largest scales, the universe is homogeneous and isotropic. In simpler terms, if you zoom out far enough, it should look roughly the same in every direction, with no special places and no structures larger than a certain size. That theoretical cutoff, the scale at which the lumpiness of the cosmic web finally blends into a smooth cosmic soup, is called the end of greatness. For decades, cosmologists believed this transition happened at around 300 million light-years. At that scale, the great walls and vast voids would average out, and the universe would finally appear uniform. Superclusters, which can span 500 or 600 million light-years, were thought to be pushing that boundary, the last great features before smoothness began. This principle is not just philosophical, it is the bedrock upon which our models of the Big Bang and cosmic expansion are built. Our entire understanding of the universe's history assumes we are not in a special location, that our view is representative of the whole. But then, astronomers kept finding candidates that seemed to break the rule. The most famous challenger is known as the Hercules Corona Borealis Great Wall. Discovered by mapping gamma-ray bursts, the most violent explosions in the universe, this purported structure was reported to stretch an almost incomprehensible 10 billion light-years across. That is more than a tenth of the observable universe. If confirmed, it would not just be a wall, it would be a continent so vast it would make the cosmic web itself look like a local pattern. Its existence would force a profound and unsettling revision of the cosmological principle. It would suggest that the universe is not smooth on the largest scales we can observe, that there are structures so immense they hint at an even grander, unseen architecture. The discovery, however, remains one of the most heated debates in modern cosmology. The method of using gamma-ray bursts as tracers is indirect and controversial. These bursts are incredibly rare, and their distances are difficult to pin down with perfect accuracy. Critics argue that the apparent concentration could be a statistical fluke, a chance alignment of bursts that paints the illusion of a wall where none exists. They point to more complete galaxy surveys, which have not yet revealed a galaxy structure of that staggering size. The Hercules Corona Borealis Great Wall sits in a tantalizing limbo, a ghost in the data, neither fully confirmed nor entirely dismissed. Its story highlights the tension at the frontier of discovery between our elegant theoretical principles and the messy, surprising reality of the cosmos. It asks a fundamental question: is the end of greatness a real physical limit, or merely a limit of our current maps? As our surveys probe deeper and wider, we are testing that boundary with every new observation, searching for the true signature of smoothness or the shocking outline of something greater. The ancient light of the cosmic microwave background is more than a baby picture of the universe. It is a dynamic screen upon which the shadows of later structures are cast. This is the Sunyaev-Zeldovich effect, a subtle but powerful interaction between the present and the primordial past. As the faint afterglow from the Big Bang travels for billions of years to reach our telescopes, its journey is not through empty space. It must pass through the vast, hot oceans of gas that fill galaxy clusters, gas heated to tens of millions of degrees. When the low-energy photons of the cosmic microwave background encounter the energetic electrons in this superheated gas, a tiny transfer of energy occurs. The photons get a slight kick, scattering to higher energies. From our perspective, this creates a distinct shadow on the cosmic microwave background map. The cluster appears as a small, subtle cold spot against the warmer background because those specific photons have been scattered out of our line of sight. It is as if a cosmic cloud has passed in front of the sun, casting a cool, precise shadow on the ground. This shadow is a gift to astronomers because its strength depends only on the density and temperature of the hot gas in the cluster, not on how far away the cluster is. That makes it a perfect tool for finding the most massive, distant clusters in the universe, piercing through dust and distance with equal ease. Surveys using this effect have catalogued thousands of previously hidden clusters, mapping the densest nodes of the cosmic web across immense stretches of time and space. But one shadow stands out from all the rest, a mystery written directly into the cosmic microwave background itself. In the southern constellation of Eridanus, there exists a vast, anomalous region known simply as the CMB cold spot. It is significantly larger and colder than standard models of the universe's infancy can easily explain. One compelling theory links it directly to the large-scale structures we have been exploring. The hypothesis suggests this cold spot might be the imprint of an immense supervoid, a cosmic desert perhaps 1 billion light-years across, lying between us and the surface of last scattering. If such a void exists, photons from the cosmic microwave background passing through it would lose a tiny amount of energy as they climb out of its shallow gravitational well, a process known as the integrated Sachs-Wolf effect. This would make that region of the sky appear slightly colder. It would be a cosmic shadow cast not by a dense cluster, but by a staggering absence, a fingerprint of the largest scale emptiness on the oldest light we can see. The search for this proposed Eridanus supervoid is ongoing, a testament to how the universe's present-day architecture can leave its ghostly signature on its own creation story, connecting the voids of today to the whispers of the first dawn. Gravity is not the only invisible force weaving through the cosmic web. Stretching between the great walls and through the silent voids is another, more elusive presence, cosmic magnetism. We have long known that planets, stars, and even entire galaxies possess magnetic fields, but the revelation that these fields might span the filaments of the cosmic web itself is an emerging secret of staggering proportions. These are not the neat, orderly fields of a simple bar magnet, but vast, turbulent seas of magnetic energy woven into the very fabric of intergalactic space. Their origins likely reach back to the universe's infancy, to tiny seed fields generated in the chaotic plasma of the first moments. As the cosmic web formed, these faint seeds were stretched, twisted, and amplified by the colossal motions of gas flowing along the filaments and crashing into the nodes where clusters form. It is a process of cosmic dynamos operating on the grandest possible scale, where the slow churn of structure formation itself generates magnetic power. The influence of these vast fields is subtle but profound. They can guide the collapse of gas clouds, influencing the birthplaces of new stars within galaxies. They act as cosmic highways and roadblocks for high-energy particles called cosmic rays, steering these mysterious messengers across millions of light-years. Most importantly, they are a testament to a fundamental truth that the empty spaces between galaxies are not truly empty, but filled with dynamic, energetic processes. To detect a magnetic field in the near-perfect vacuum of a cosmic filament is an extraordinary challenge. Astronomers cannot see it directly, so they must observe its effect on something they can see, light. They use a phenomenon called Faraday rotation. When polarized light waves vibrating in a specific plane, travels through a magnetized medium, its polarization angle slowly twists. The stronger the magnetic field and the longer the path through it, the greater the rotation. By observing distant quasars and galaxies whose light has passed through the web's filaments, and meticulously measuring how that light's polarization has been altered, scientists can map the presence and strength of these invisible fields. It is like deciphering a message written in the subtle twist of starlight. Each measurement is a data point in a map of cosmic magnetism, slowly revealing how this hidden force is integrated into the architecture of everything, a silent partner to gravity in shaping the story of our structured universe. For all its breathtaking structure, the universe held onto a final, embarrassing secret about its own inventory. Cosmologists had a precise accounting from the cosmic microwave background of how much ordinary matter, the protons and neutrons that make up stars, planets, and us, should exist in the cosmos. Yet when they tallied everything they could see, all the galaxies, stars, and cool gas, the numbers came up short by a staggering amount. Roughly half of all the ordinary matter in the universe was simply missing. This was the missing baryon problem, a glaring hole in our understanding of cosmic contents that persisted for decades. The solution, it turns out, was hiding in plain sight, woven into the very fabric of the cosmic web. The missing matter was not in dark, cold clumps, but spread thinly through the filaments as an immensely hot, diffuse gas. Astronomers call it the warm-hot intergalactic medium, or the WHIM. This is a plasma heated to temperatures between 100,000 and 10 million degrees, a searing but incredibly thin fog that permeates the spaces between galaxy clusters. Finding something so hot yet so diffuse is one of observational astronomy's greatest challenges. It does not glow brightly enough to be seen directly with most telescopes. To detect it, scientists again turned to the technique of cosmic backlighting, but this time they needed to look in two different parts of the spectrum. When the light from a distant quasar passes through a filament of the WHIM, the superheated gas leaves a dual fingerprint. The highly ionized oxygen and other heavy elements within the plasma absorb specific wavelengths of ultraviolet light. By studying the intricate absorption lines in quasar spectra from space telescopes like Hubble, astronomers can trace the cooler components of this web. For the hotter, more energetic gas, they look to X-ray observatories. The million-degree plasma emits a faint, specific X-ray signature when highly charged iron and other ions interact. It is an incredibly subtle signal, like trying to hear a whisper in a hurricane. By combining thousands of observations of different quasars and deep X-ray exposures, a picture has slowly emerged. The missing half of all normal matter is not missing at all. It is all around us, a vast, hot atmosphere filling the cosmic web. This discovery closed one of cosmology's most persistent gaps, confirming that our inventory of the universe is at last complete. The glittering galaxies are just the condensed knots in a universal ocean of thin, scorching gas, the true reservoir of the ordinary stuff from which everything we know is made. This grand cosmic architecture has a fatal flaw, a built-in expiration date written into the very fabric of space. The intricate web of filaments and superclusters, the majestic dance of galaxies toward immense attractors, is a temporary arrangement in a universe whose ultimate fate is one of profound isolation. The force orchestrating this slow-motion dissolution is dark energy, the mysterious repulsive pressure that causes the expansion of the universe to accelerate. For billions of years, gravity has been the master builder, patiently gathering matter into the magnificent structures we see today. But dark energy is the great unraveler working on a far longer timeline. Its influence is subtle but relentless, like a constant, gentle breeze that grows stronger over eons. Right now, within our local group of galaxies, gravity still holds absolute dominion. The Milky Way and Andromeda are destined to merge in a few billion years, their gravity binding them together forever. But look beyond our immediate family and the story changes. The space between galaxy clusters within a supercluster like Laniakea is already vast, and it is within these immense gaps that dark energy gains its foothold. As the acceleration continues, the expansion of space itself within these superclusters will begin to outpace the gentle gravitational pull that loosely binds them together. The great rivers of galactic flow, currently all streaming toward the Great Attractor, will first slow to a halt. Then they will reverse. The filaments of the cosmic web, those glorious superhighways of gas and galaxies, will begin to stretch and thin. Over tens of billions of years, they will be pulled apart from within. Imagine a magnificent spiderweb caught in a steadily strengthening wind. First, the delicate connections between the thicker strands begin to snap. Then the strands themselves stretch and break until only isolated knots of silk remain, drifting ever further apart. This is the future of Laniakea. The supercluster will not explode, it will simply come undone. The Virgo cluster, the Norma cluster, all the great gravitational anchors will find their connections severed. Each will become an isolated island universe, adrift in a rapidly expanding sea of nothingness. The consequences for any future astronomers are staggering. As space between these structures expands faster than light can cross it, the galaxies outside our gravitationally bound local group will begin to vanish. Their light, stretched to longer and longer wavelengths, will first redshift into invisibility. Then, as the expansion rate exceeds the speed of light across those vast distances, the galaxies will cross a cosmological event horizon. They will not explode or die, but they will simply disappear from our observable universe, their signals forever cut off from us. The night sky for any civilization in the far future will be profoundly empty. The great attractors and shimmering walls will be myths from an ancient, unimaginably rich past. Our descendants will see only the merged stars of our own galaxy and its closest bound companions, surrounded by an infinite black void. All evidence of the cosmic web, the large-scale structure that defined the universe's adolescence, will be erased from their view. The universe's story will have moved from a chapter of connection and construction into one of eternal, silent separation. The Great Attractor is not a lurking cosmic monster. Its true identity, pieced together from decades of observation, is both more complex and more elegant. It is the gravitational heart of our home supercluster, Laniakea. Picture the slow, stately flow of 100,000 galaxies, all sliding down the gentle slopes of space-time toward a single, invisible basin. That basin's deepest point, the place where the cosmic watershed of our entire region converges, is the Great Attractor. It resides in the direction of the Norma cluster, a massive gathering of galaxies itself, but it is more than just that cluster. It is the densest knot in our local web, the point where several of Laniakea's major filaments intersect and pool their immense collective mass. This modern understanding resolves the mystery. The Great Attractor is not a singular, anomalous object like a supermassive black hole grown to impossible size. It is a supercluster core, a natural and inevitable feature of the universe's architecture. Its immense gravitational pull is simply the sum of all the mass in that concentrated node, a combination of the Norma cluster's visible galaxies and, far more importantly, the titanic halo of dark matter that anchors the entire region. This makes it a sibling to other great gravitational centers, like the core of the Coma cluster or the heart of the Shapley supercluster. Each is a major metropolitan hub in the cosmic web, some larger, some smaller. Ours just happens to be the one we are falling toward, making it feel uniquely significant. This realization is a profound shift in perspective. We are not being devoured by a hidden beast. We are simply residents of a vast continent, flowing along its rivers toward its central valley. The Great Attractor is that valley, the quiet, inevitable destination for everything in our local universe. That subtle drift of our galaxy, the 630 kilometers per second toward Centaurus, is far more than a simple speed. It is a peculiar velocity, a crucial fingerprint left at the cosmic crime scene. Every galaxy has two motions. The first is the grand, smooth expansion of the universe itself, the Hubble flow, which carries galaxies apart like raisins in an expanding loaf of bread. The second is this peculiar velocity, a local deviation from that smooth expansion, a personal drift caused by the gravitational tugs of nearby massive structures. It is the difference between floating down a wide, calm river and being nudged by a hidden current. By the 1970s, astronomers measuring galaxy redshifts expected to see a neat, orderly pattern, a perfect Hubble flow where more distant galaxies recede faster. Instead, they found a messy, beautiful reality. The redshifts were scrambled. Our entire local neighborhood of galaxies was not just receding, it was also sliding sideways, all of us sharing this peculiar velocity toward the same patch of darkness. This was the telltale sign. You cannot see the hidden mass directly, but you can see how it makes everything else move. By meticulously mapping the directions and speeds of thousands of galaxies, scientists could reverse engineer the gravity that must be causing it. They began to construct a cosmic velocity field, a three-dimensional map of flows. Think of it as charting the wind by watching how every leaf in a forest drifts. Each galaxy's peculiar velocity is a tiny arrow pointing toward the greatest source of gravitational pull in its vicinity. When you plot all these arrows, they don't point randomly. They converge like iron filings lining up around a magnet. Those streams of galactic motion revealed the contours of hidden mountains of mass, the gravitational landscape of our corner of the cosmos. The Milky Way's specific motion, combined with the motions of countless other galaxies, all pointed insistently toward that one obscured region. This velocity map became the primary evidence for the Great Attractor's existence long before we could see through the zone of avoidance. It proved that the pull was real, immense, and affected galaxies across a volume hundreds of millions of light-years wide. More profoundly, it revealed that the amount of visible matter in that direction was utterly insufficient to explain the strength of the flow. The peculiar velocities were tracing something far greater than the sum of the stars. They were mapping the invisible scaffold of dark matter itself. Every deviation from the Hubble flow is a direct measurement of gravity's work, a whisper from the hidden architecture that guides our journey through the void. The conquest of our cosmic blind spot has become one of modern astronomy's quiet triumphs. Where optical telescopes once saw only a starry fog, new eyes have now peeled back the veil, revealing the hidden architecture in stunning detail. This transformation is thanks to space-based observatories designed to see the universe in wavelengths our eyes cannot. NASA's Wide-Field Infrared Survey Explorer, or WISE, was a pioneer in this effort. Launched in 2009, its mission was to map the entire sky in infrared light. Infrared radiation, with its longer wavelengths, slips between the dust grains that block visible light, much like heat from a warm house can be felt through a frosty window. WISE's all-seeing infrared gaze systematically scanned the zone of avoidance, detecting the faint glow of millions of stars and galaxies previously shrouded by the Milky Way's bulge. It was not looking for individual wonders, but mapping the background glow of stellar populations, the collective light that traces the mass distribution behind the dust. The data revealed the outlines of entire galaxy clusters and vast stellar streams, confirming that the hidden universe was just as richly structured as the parts we could see. But to weigh the true gravitational anchors, scientists needed another perspective. Enter the European Space Agency's Planck satellite. While its primary mission was to study the cosmic microwave background with unprecedented precision, its all-sky maps at microwave frequencies delivered an unexpected bonus for the hunt. Planck's instruments were exquisitely sensitive to the Sunyaev-Zeldovich effect, that subtle shadow that galaxy clusters imprint on the ancient light. By scanning the entire sky, Planck could detect these shadows even in the crowded zone of avoidance, identifying massive clusters solely by the hot gas they contained, regardless of dust obstruction. The combined power of these missions has been revelatory. Where our maps once showed a blank, mysterious band across the sky, we now see a detailed landscape. Images constructed from WISE and Planck data show dozens of previously hidden galaxy clusters glittering like jewels on black velvet, strung along filaments that weave behind the plane of our galaxy. They paint a definitive, high-resolution picture of the mass concentration in the Norma region. We can now see that the Great Attractor is not a solitary giant, but the brilliant, dense core of a sprawling network, a gravitational nexus where several major filaments of the cosmic web converge and tangle. This is no longer inference from motion alone, it is direct observation. The hidden valley that pulls us has been photographed, its topography charted. Every new cluster revealed adds weight to the gravitational models, helping astronomers precisely balance the ledger of what is pulling us and from where. The zone of avoidance, once a fortress of ignorance, has been breached, and its secrets are now the foundation of our most accurate maps of the local universe. The final proof of the cosmic web's existence came not from a telescope but from a machine. To truly test our understanding of the universe, scientists had to learn how to build one from scratch. This is the power of numerical simulations, the virtual laboratories where entire cosmos are born and evolve inside supercomputers. The process begins with the most humble of seeds, the tiny temperature ripples mapped in the cosmic microwave background. In the simulation, these ripples are translated into an almost perfectly smooth, three-dimensional grid, with infinitesimal variations in density placed at random, matching the precise statistical pattern observed in the ancient light. Into this grid, the programmers pour trillions of invisible particles, each one representing a parcel of dark matter. Then they set the clock to run from just after the Big Bang, and they let the only rule be gravity. As the virtual universe begins to expand, gravity gets to work. Those slightly denser patches attract more dark matter particles. Over millions of simulated years, the gentle tug pulls particles into delicate threads. The threads merge and thicken into filaments, while the emptier regions drain and grow into vast voids. Where filaments cross, dense knots form, becoming the seeds of future galaxy clusters. This is the N-body simulation, a breathtaking digital dance of pure gravity and dark matter. It produces a cosmic web in silico that looks hauntingly familiar, a ghostly skeleton of interconnected strands. But a skeleton is not enough. The next generation of simulations, with names like Illustris and Eagle, added the messy physics of normal matter, the baryons. They incorporated the complex behavior of gas, modeling how it heats, cools, flows along the dark matter filaments, and eventually collapses to form stars and galaxies. They added the furious energy of supernova explosions and the voracious appetite of supermassive black holes, forces that can heat gas or blow it out of galaxies, regulating star formation. Running these simulations requires staggering computational power. The Illustris TNG project, for instance, used over 24,000 computer cores running continuously for months, tracking the evolution of tens of billions of particles representing both dark and normal matter across more than 13 billion years of cosmic time. The result is not just a static image, but a dynamic movie of cosmic evolution. You can watch a virtual universe grow up from a smooth, primordial haze into a structured, web-like network, complete with glittering galaxies that form, merge, and age in the dense regions along the filaments. The most profound moment comes when scientists hold these virtual universes up beside our real maps from the Sloan Digital Sky Survey. The resemblance is uncanny. The statistics match, the filamentary patterns align, the distribution of galaxy clusters and voids corresponds. The simulated universes spontaneously produce structures that look just like the Great Wall, the Boötes Void, and the dense nodes akin to the Great Attractor. This agreement is perhaps the strongest validation we have for our entire cosmological model, the lambda-cold dark matter paradigm. It tells us that if you start with the initial conditions of the Big Bang, add the ingredients of dark matter and dark energy, and apply the known laws of physics, the universe that emerges will look, in its essential architecture, exactly like the one we live in. The computer did not know about the Great Attractor. It simply calculated gravity's consequences, and the attractor appeared. In these digital universes, the mystery of our large-scale structure is not a mystery at all, but an inevitable outcome. The universe's blueprint was shaped by the most elusive architects of all. Billions of years before the first stars ignited, the cosmos was flooded with a sea of ghostly particles, neutrinos, created in the unimaginable heat of the Big Bang's first second. Today, they still stream through every inch of space and through you at nearly the speed of light, a whisper from creation itself. This is the cosmic neutrino background, and while each particle is almost massless, their collective story is etched into the large-scale structure we see. In the universe's first moments, neutrinos ruled. For a brief, critical period, they were so energetic and numerous that they dominated the cosmic energy budget, moving so fast they could escape the gravitational pull of any nascent clump of matter. This created a fascinating cosmic competition. Dark matter and normal matter, moving sluggishly by comparison, wanted to collapse under gravity to form the seeds of the web. But the neutrinos, these fast-moving ghosts, were smoothing everything out, washing over those tiny density ripples and suppressing their growth. It was like trying to build a sandcastle while a gentle but persistent tide keeps washing the grains away. The neutrinos' incredible speed gave them a sort of gravitational pressure, preventing them from clustering on small scales. This left a specific, subtle signature on the emerging cosmic web. The overall pattern of filaments and voids we see today is the same, but the distribution of matter within that pattern is different. Because of the neutrinos' early smoothing effect, there are slightly fewer of the very smallest galaxy clusters and dwarf galaxies than there would be in a universe without neutrino mass. They sculpted by absence by gently holding back the growth of the tiniest structures. We cannot catch these relic neutrinos directly with any current detector. They are simply too low energy. But we can see their ghostly handiwork. Cosmologists search for this signature by comparing incredibly detailed maps of the cosmic web, from surveys like the Dark Energy Spectroscopic Instrument with predictions from supercomputer simulations. The simulations can be run with different assumed masses for neutrinos. By finding which simulated universe with which neutrino properties best matches the real observed clustering of galaxies and the statistics of the cosmic microwave background, scientists can weigh the universe's neutrino background indirectly. It is a cosmic forensic investigation where the arrangement of galaxies across billions of light years serves as evidence of particles that passed through them over 13 billion years ago. This work has yielded a profound result. We now know neutrinos must have a tiny mass because their gravitational influence is written into the cosmos. These faintest of sculptors, born in the first instant of time, helped decide how the universe would clump, leaving their indelible, almost imperceptible mark on the grand design of everything. The pull of the Great Attractor forces us to confront a radical possibility. What if our understanding of gravity itself is incomplete? For decades, the dominant explanation for such immense, unseen gravitational influence has been dark matter, an invisible form of matter that outweighs the normal kind by a factor of 5 to 1. But a small, persistent group of physicists proposes a different path. They suggest that perhaps there is no dark matter at all. Instead, gravity might simply behave differently on the vast scales of galaxies and superclusters than Isaac Newton or Albert Einstein predicted. This idea is known as modified Newtonian dynamics, or MND, and its proponents see the Great Attractor not as proof of dark matter, but as a potential clue to a deeper law of nature. The core argument is one of elegance. Why invent an entirely new, invisible substance that has never been directly detected in a lab, when you could instead modify the equations of a force we already know? Mann proposes that in regions of extremely weak gravity, like the outskirts of galaxies or the spaces between clusters, the force of gravity does not fade as quickly as the traditional inverse square law says it should. It gets a small, persistent boost. This tiny modification can, in theory, explain why stars at the edges of spiral galaxies orbit just as fast as those near the center, a phenomenon traditionally attributed to a halo of dark matter. Applied to the Great Attractor, the idea is that the coordinated flow of thousands of galaxies might not require a hidden mountain of dark matter in Norma. It could be the natural result of gravity's enhanced strength over these immense intergalactic distances, pulling on the visible galaxies more strongly than our standard models allow. It is a compelling narrative of scientific parsimony, asking if we have been overcomplicating the cosmos by filling it with ghosts, when the real answer might be a subtle tweak to a fundamental force. The debate, however, is decided not by philosophy but by brutal observational tests, and the cosmic web provides the ultimate laboratory. One of the most powerful tests involves the behavior of galaxy clusters, especially when they collide. Observations of a system known as the bullet cluster show two clusters that have passed through each other. The hot X-ray emitting gas from each cluster, which makes up most of its normal matter, was slowed by friction and now lags behind. But gravitational lensing maps show the bulk of the mass which bends light has sailed ahead with the galaxies. This is interpreted as the dark matter, which does not interact with anything but gravity, moving unimpeded. Mann, in its basic form, struggles to explain this clean separation of mass from the visible gas without invoking some form of unseen matter, which would defeat its original purpose. Furthermore, the precise patterns of the cosmic microwave background and the large-scale clustering of galaxies are exquisitely matched by supercomputer simulations that include dark matter. Reproducing this detailed cosmic web with a modified gravity theory alone has proven extraordinarily difficult. The peculiar velocities of galaxies flowing toward attractors also pose a challenge. While Mann can potentially explain some individual galaxy rotations, crafting a coherent model that accounts for the specific, intricate flow patterns of thousands of galaxies across hundreds of millions of light years, all pointing towards specific mass concentrations like the Great Attractor and Shapley, is a monumental task. Most cosmologists argue that the dark matter model, for all its strangeness, simply fits the totality of the data better. It provides a single, unifying framework that explains the cosmic microwave background, the formation of the cosmic web, the motions within galaxies, and the dynamics of clusters all at once. The existence of structures like the Great Attractor, with its gravitational pull far exceeding its visible light, remains a cornerstone of that evidence. Yet the minority view persists, driven by the noble scientific instinct to question foundational assumptions. The mystery of the attractor, therefore, is not just about what is pulling us, but about the very nature of the force that binds the universe together. It stands as a challenge to both sides, a complex gravitational puzzle that any successful theory of the cosmos must ultimately solve. The maps we have now are already revolutionary, but they are merely the first rough sketches of a continent we have only glimpsed. To uncover the universe's deepest architectural secrets, we need a new generation of cartographers, instruments of such power they will redefine the very act of observation. This is the dawn of a new golden age in cosmology, led by three titanic projects poised to scan the heavens: the Vera C. Rubin Observatory, currently under construction in Chile, will house the Legacy Survey of Space and Time, or LSSD. Its primary mirror is over 8 meters wide, and its camera is the size of a small car, containing 3.2 billion pixels. Every few nights for a decade, it will capture the entire visible southern sky in astonishing detail, creating a dynamic, living movie of the cosmos. It will not just take a snapshot, it will watch for change, detecting billions of galaxies and millions of transient events like supernova. Its immense statistical power will allow scientists to construct the most detailed three-dimensional map of the cosmic web ever made, tracing the distribution of normal matter with unprecedented fidelity. But to weigh the invisible skeleton, we need a different kind of vision. The European Space Agency's Euclid spacecraft, now in orbit, is designed to map the geometry of the dark universe. It will peer across 10 billion light-years, measuring the shapes of over 1 billion galaxies. Why their shapes? Because of an effect called weak gravitational lensing. As light from these distant galaxies travels to us, it passes through the warped space-time around filaments and clusters of dark matter. This subtly distorts the galaxy's images, stretching them in a coherent pattern. By measuring these tiny, systematic distortions across the sky, Euclid will create a direct mass map of the dark matter web, revealing its filamentary structure in exquisite detail. It will essentially take an X-ray of the cosmos's hidden bones. Meanwhile, NASA's Nancy Grace Roman Space Telescope, set to launch later this decade, will combine immense power with a staggeringly wide field of view. It will perform ultra-deep surveys to find the most distant supernova, refining our measurement of the universe's expansion, and conduct high-resolution surveys of galaxy shapes to complement Euclid's work. Together, these observatories represent a quantum leap. They will map not millions but billions of galaxies, charting the cosmic web across immense volumes of space and time. This will let us see the universe's structure evolve, watching how filaments thicken and voids expand over cosmic epochs. What might they find? They could reveal attractors even greater than Shapley, hidden in other blind spots or at distances we cannot yet probe. They might discover wrinkles in the web so vast they challenge the cosmological principle anew, or pinpoint the subtle signatures of primordial neutrinos and other exotic particles in the clustering of galaxies. Most importantly, by cross-referencing the visible galaxy maps from Rubin with the dark matter mass maps from Euclid and Roman, we will perform the ultimate test of our cosmic models. We will see with crystal clarity how perfectly the luminous cities of stars trace the invisible scaffolding of dark matter. Any mismatch, any place where the light and the mass do not align as predicted, could be the crack that leads to a new physics. These are not just telescopes, they are time machines and forensic tools, built to read the fine print on the blueprint of everything. Our ability to map this cosmic architecture leads to a deeper, more unsettling question. Why does this specific web exist at all? The delicate balance required for its formation points toward a philosophical secret known as the anthropic principle. It begins with those initial quantum ripples, the seeds planted in the first fraction of a second. Their amplitude, their strength was not random, it was precisely tuned. If those primordial density fluctuations had been just slightly weaker, gravity would have had almost nothing to work with. Matter would have spread itself too thinly, never gathering into distinct filaments and nodes. Galaxies would have failed to condense, stars would never have ignited, and the universe would be a dark, formless sea of diffused gas. There would be no cosmic web, no great attractor, and certainly no one to wonder about it. Conversely, if those initial ripples had been just slightly stronger, gravity's pull would have been catastrophic. Matter would have clumped together with ferocious efficiency, rapidly collapsing into a universe dominated by monstrous black holes and dense, chaotic knots. The elegant, sprawling network of filaments and voids would never have had a chance to form, the universe collapsing back on itself or tearing apart in a frenzy of early structure. The window for a universe like ours, one capable of weaving a web and lighting stars within it, is astonishingly narrow. This fine-tuning feels like a cosmic coincidence of breathtaking precision. So why is our universe so perfectly set up for complexity? The anthropic principle offers a stark, almost circular answer. we can only observe a universe capable of producing observers. If the constants and conditions were not just right, we would not be here to measure them. This shifts the question from why this universe to why we are in this particular universe. This line of thinking opens the door to a staggering possibility, the multiverse. In this view, our cosmos with its specific web is not the only one. It could be one bubble in an infinite froth of universes, each with different physical constants, different strengths for those initial ripples. Most of those universes would be stillborn or barren, incapable of generating structure or life. But by pure chance, a few, like ours, would land in the Goldilocks zone where galaxies can form and thinking beings can evolve. We find ourselves in a web not because it was designed, but because it is the only kind of web that allows us to be here to see it. It is a humbling and to some an unsatisfying answer, yet it forces us to confront the scale of our mystery. The Great Attractor is not just a local landmark, and the cosmic web is not just a beautiful pattern. They are the direct, necessary consequences of a universe fine-tuned for existence itself. A single thread in a tapestry whose very possibility seems almost too perfect to be an accident. The filaments of the cosmic web are not pristine. They carry the chemical memory of stellar cataclysms, a form of intergalactic pollution that has been seeding the void for billions of years. Within the fiery hearts of massive stars, nuclear fusion forges the lighter elements of the early universe, hydrogen and helium, into heavier ones like carbon, oxygen, silicon, and iron. When these stars reach the end of their lives, they do not fade quietly. They explode as supernova, blasting these newly forged elements out into their host galaxies with unimaginable force. But the story does not end there. The most energetic galaxies, those powered by voracious supermassive black holes as quasars, generate winds that can sweep entire galaxies clean of their gas. These titanic outflows act like cosmic bellows, blowing enriched material far beyond a galaxy's gravitational grasp, directly into the intergalactic medium that fills the filaments of the web. This process is a fundamental form of cosmic recycling. The empty spaces between galaxies are not truly empty. They are a reservoir, a dumping ground for the ashes of dead stars and the exhaust of galactic engines. Over cosmic time, this pollution has fundamentally changed the composition of the universe. The primordial gas that condensed into the first galaxies was pure hydrogen and helium. But the gas that will fuel the formation of future stars, the gas currently flowing along the filaments, is now laced with these heavy elements, the very building blocks of planets and life. Astronomers can read this chemical history written in the light of the most distant beacons. When they point their telescopes at a quasar billions of light years away, they are not just looking at the quasar itself. They are using its brilliant light as a cosmic flashlight, illuminating everything that lies between it and us. As that light travels through the filaments of the warm, hot intergalactic medium, the heavy elements within that gas, the carbon, oxygen, and iron, absorb specific, unique wavelengths of the quasar's light. The resulting spectrum, when broken down into a rainbow of colors, is scarred by a forest of dark absorption lines. Each line is a barcode, a chemical signature. A specific dip at a precise wavelength tells an astronomer that a cloud of ionized carbon, for example, lies at a specific distance along that line of sight. By analyzing this intricate pattern, scientists can not only map where these elements are, but also determine their temperature, density, and motion. They have found that this enriched gas is everywhere, tracing the very filaments that define the cosmic web. This means the grand architecture we see is also a chronicle of galactic life and death. Every filament is a museum, its diffused gas holding the fossilized remains of countless supernovae and the echoes of quasar winds from epochs long past. The oxygen we breathe, the iron in our blood, was once scattered across millions of light years of intergalactic space, riding the currents of the web before being gathered into a new generation of stars and planets. Our existence is tied to this vast, polluted network, a testament to the fact that even the greatest voids are connected to the lives of galaxies. This immense gravitational journey spans billions of years, a voyage with no final cataclysm. Our destination within the Great Attractor is not a point of cosmic consumption, but a region of profound density and connection. We are sailing with countless other galaxies toward the vibrant heart of our supercluster, a future metropolis of the cosmic web. Imagine, in 100 billion years, a civilization looking up from a world that orbits a star within the Norma cluster, at the very core of the Great Attractor. Their night sky would be a spectacle of staggering brilliance. Thousands of galaxies, drawn together by gravity over eons, would crowd the heavens, their combined light painting the darkness with a soft, eternal glow. They would live in a sky of constant celestial company, a stark contrast to our own relatively isolated view. And if they turned their most powerful telescopes back toward the path we traveled, what would they see? They might glimpse the faint, redshifted glow of a single colossal galaxy where our local group once was. The Milky Way and Andromeda, having long since completed their majestic merger, would appear as a distant, aging island universe, receding into the deepening cosmic night as the expansion of space carries it away from the attractor's bound core. For that future civilization, the great mystery would not be what is pulling them, for they would reside within it. Their questions would be grander. They would study the intricate orbits of galaxies within their dense cluster, a dynamic dance we can only theorize about. They would probe the properties of the superheated gas that fills their intergalactic space, and they might even detect the faint gravitational echoes of smaller structures still falling into their colossal home. They would have a front row seat to the final acts of hierarchical assembly, watching as the last straggler galaxies are absorbed, completing the formation of a single, gargantuan elliptical galaxy that will stand as the enduring legacy of Laniakea's core. Our journey, then, is not toward an end, but toward a new beginning of understanding. The Great Attractor pulls us toward a future of deeper cosmic connection, a place where the secrets of galaxy clusters and dark matter can be studied not from a distance, but from within. It is a reminder that our universe is not static, but a story of perpetual motion and rearrangement. We are temporary passengers on a filament of the web, granted a brief glimpse of the architecture as we flow along its currents. The ultimate purpose of this voyage is simply to be part of the universe's endless evolution, to witness one chapter in the slow, beautiful gathering of light. The journey through these 30 secrets has taken us from a single, hidden pull to the blueprint of everything. We began with the local mystery of the Great Attractor, a gravitational anomaly felt long before it was seen, and followed its clues outward into an immensity we are only beginning to chart. We discovered that this attractor is not a monster, but the heart of our home supercluster Laniakea, a single valley in a landscape of unimaginable scale. We pierced our own galactic blind spot to find hidden clusters, mapped the vast spongework of filaments and voids, and learned that half the universe's normal matter was hiding in a thin, hot fog within those threads. We saw how dark matter's invisible skeleton dictates the form of this cosmic web, how dark energy will one day tear it apart, and how our very presence here is a testament to a universe fine-tuned for complexity. This architecture tells the complete story of our cosmos, from the frozen sound waves of the Big Bang to the silent, accelerating future. It is a story written in gravity, light, and the slow, patient flow of time. So the next time you stand under a clear night sky, remember what you are truly looking at. You are not seeing random specks of light. You are gazing out through the local filament of a universal web, toward the glowing nodes of distant superclusters and the profound darkness of ancient voids. You are a witness to a dynamic, evolving structure of breathtaking grandeur. We want to hear which part of this journey shifted your perspective the most. Was it the hidden hand of dark matter, the fate of superclusters unraveling, or the simple, stunning fact that we are sailing on a river of galaxies? Let us know in the comments below. This grand voyage across the cosmic web is not just a story of distant giants, it is also the story of where you are right now. Let us write your full cosmic address, a reminder of the breathtaking layers of scale that contain our tiny, precious vantage point. You are here on Earth, a vibrant world of water and rock. You are in the solar system, orbiting a stable, middle-aged star we call the Sun, one of perhaps hundreds of billions in our galaxy. Our system resides on a minor spiral arm known as the Orion Spur, a side street in the vast, disc-shaped metropolis of the Milky Way galaxy. This galaxy, with its 400 billion stars, is itself a citizen of a small, gravitationally bound family, the local group, which includes the Great Andromeda galaxy and dozens of smaller companions, all orbiting a common center of gravity. This entire family is a province within the sprawling Virgo supercluster, a collection of about 100 galaxy groups, all slowly falling toward the massive Virgo cluster at its heart. And we now know that Virgo itself is but one lobe of something far greater, the Laniakea supercluster, an immeasurable heaven of 100,000 galaxies, all flowing down the same gentle gravitational slopes. The destination of that flow, the deepest basin in our local universe, is the Great Attractor. So your address concludes with a direction of travel. You are within the Laniakea supercluster, heading toward the Great Attractor. This means you are not merely standing on a planet. You are a passenger on a spaceship Earth, a vessel carrying you through multiple layers of motion. You are spinning on Earth's axis, orbiting the Sun, orbiting the center of the Milky Way, moving with our galaxy through the local group, and sailing with our entire supercluster down the cosmic watershed toward a hidden valley of gravity. Every single moment you are riding these nested currents, a participant in the slow, stately dance of the universe's grandest design. To know this address is to understand your true context, a perspective that transforms the familiar ground beneath your feet into the deck of the most incredible vessel imaginable, journeying through an ocean of stars and dark matter, forever guided by the invisible architecture of everything.